Okay, so in today's lecture, we are now again continuing the concept of your two-part test. Before that, in lecture one, we did the limit of limit of function fxy, limit of function fxy, and we did it like this one, that if xy approaches to x naught y naught, then fxy approaches to L, and L, the value that comes out to be, it should be finite and unique. So we say limit of fxy is equal to L, and as when we say this, when fxy approaches to L, as xy approaches to x naught y naught point. And for single variable, we did like this one, that the limit of function fx is L if fx approaches to L as x approaches to x naught. So the basic difference between the limit of function in two variables and limit of function in a single variable is that in single variable you approach to the point x naught from left hand side and right hand side. This is the only possibility, and that is why we find left hand limit and right hand limit, and we say that the values of these two limits as we approach x naught from left or right, the value should be same, the value of limit should be same. However, in the case of your two variable function, when we are approaching the point x naught y naught, then in that case we can approach the point x naught y naught from any direction, not from left and right, because the point x naught y naught is somewhere in the plane. So it can be approached from any of the direction, and the path which we are saying, that can be line, that can be curve. So that is the basic difference of the limits in two variable and single variable, where in a two variable you can approach the point from any of the direction, and the main condition is that whatever path you follow to approach point x naught y naught, the value should be same, and on the basis of that we defined two-part test. For checking the non-existence of limits. So two-part test was based on the theory that if we can find the two paths, such that limit from those two paths is different, then limit will not exist. Why? Because if limit exists, then it should be same from whatever path we are approaching that point x naught y naught. So continuing this concept of two-part test, we are again now here considering one more question. Check whether the function fxy is equal to x square plus y upon x square minus y when xy is not equal to 0, 0, and 0 when xy is equal to 0, 0, is continuous or not at point 0, 0. So here you have to find or check whether the given function is continuous at the given point 0, 0 or not. So using the definition of continuity, clearly fx is defined at 0, 0 as given above. You can see the function is defined at 0, 0. So the first condition for the continuity of function is done. Coming to the second condition, that we need to check that the limit at point 0, 0 of this function fxy, it exists or not. So this is the second point which we have to consider, that whether the limit of a given function exists at 0, 0 or not, second condition for continuity. So for that, since your function is like this one, x square plus y upon x square minus y. So considering this function, we choose a path such that first thing, it should pass through the point 0, 0. It should pass through the point 0, 0. And secondly, the function, whatever is given, if the path should be like the values of variable x or the terms of variable x should get cancelled from numerator and denominator. So looking at the function, or let me write here directly, choosing path such that y is equals to your mx square. I choose the path by taking into consideration 2 points. First point, it should pass through point 0, 0, and that is what it is here. Since let me write choose path y equals to mx square such that as x tends to 0, y tends to 0. So you can see the path y equals to mx square chosen by us passes to 0, 0. And second point, when we substitute this value in function, if possible, the value of or terms of variable x should get cancelled from numerator and denominator. So let us see what happens if we substitute the value of y equals to mx square in the function fxy. So in that case, we get your limit x tending to 0, your x square plus, okay, I think the value of path should be, yes, it is not should be x square, it should be mx, because then if the value of x square variables can't be cancelled. So let me take here y equals to mx, so that now it becomes your m square x square, so that it becomes your m square x square. Yes, now you can see the path chosen by you, y equals to y equals to mx square is not correct, because in that case then we will not be able to get the terms of x cancelled from numerator and denominator. So you get here limit x tends to 0, 1 plus m square, 1 minus m square, and that is 1 plus m square, 1 minus m square. So clearly limit is path dependent. Different for different values of n, not unique. So limit does not exist. Simply, you do not have to write all those things. These are just so that you can clarify the concept more. So limit is path dependent, that is, it depends upon m. It is different for different values of m, and it is not unique. Hence, you can say limit does not exist. So function is not continuous. At 0, 0. The function is not continuous at 0, 0. So in this way, you can see the condition fetching does not hold, where limit of function at 0, 0 does not exist. Hence, we can say the function is not continuous. So this is the way that we use two-part test to find the continuity, and mostly these questions are related to checking the limit of the given function and using two-part test. Now let us just look at another example. Yes, here it is. fxy is equal to x square minus y square on x square plus y square. Question is, does limit exist at 0, 0? Solution. Now here we are going to see here you can have a problem using two-part test. So in this question, if looking at the function uh, let let us approach let us approach 0 0 by path y equals to mx, y equals to mx, such that as x tends to 0, y tends to 0. So I have here limit xy tending to 0 0 fxy. This is limit x tending to 0, y equals to mx. This is x, this is x, and then you have your, this is x into x square minus y square, x square plus y square, and this gives you limit x tending to 0, x square minus m square, x square plus m square, x square. So solving this, you get this one, and clearly you can see here you get limit x tends to 0, x 1 minus m square, 1 plus m square, and this no doubt gives you 0. This no doubt gives you 0 for all m. Whatever m you choose, you get 0. So the question is here that when you are getting here 0, so is that possible now that using two-part test you can say that now this limit which now comes to be 0, which looks like it is unique and finite for all m. So on this base, can I say that the limit of this function at 0 0 exists by using two-part test, because we have actually used that. So here I have got this thing xy 0 0 fxy is equal to 0 for all m. We have chosen the path y equals to mx. Now using two-part test, at least in this case we can't say here that limit exists, just on the base that our path y equals to mx gives us limit which is infinite and unique. Why it is so? Because there are infinite many other paths from where we do not know the value of limit that comes out to be finite or unique. That is, two-part test is basically used. Two-part test is used for checking non-existence of limit. Using this two-part test to show that the limit exists, it is not possible. You can't say. Maybe in this case, whatever the function we have considered, limit exists and it is equal to 0. But from the point of two-part test, we can't say this one, because two-part test we just only says that non-existence of limit. So here by using two-part test, we can't say that limit exists. So in such cases we have to use formal definition of limits to show that whether limit exists or not. So in such cases, because two-part test is for non-existence, if in using two-part test we just only use one of the paths, it may be possible there may be infinite many other paths from which we can approach this 0 0. We have, from that infinite family, we have considered only one family of curves which approaches this 0 0. We do not know about other paths. So how we can say that limit is going to be 0? So two-part test can't be used for checking the existence of limit. It is only used for non-existence of the limit, and in such cases we have to leave these questions as such if we are using two-part test, and we have to go for the formal definition of limit that we will be doing later to check whether limit exists or not. There is another technique that we convert the Cartesian to polar coordinates and then we check the existence of limits, but again there in also that cases we have to use a formal definition of limit. So this is about your concept of two-part test, where it fails and how we can use this to find the non-existence of limits. Next comes the topic of partial derivatives. In this topic, we will be dealing with the partial derivative of a given function. Before that, just in short, what is ordinary derivative? You know all these things, but let me just start with the basic concept of ordinary derivative. Say you have a function f(x), okay, where y is your dependent variable and x is your independent variable. That is, the variable that is dependent is depending only upon one independent variable. Then you have the concept of ordinary derivative and you write the derivative as dy dx, y dash, f dash x. So this is basically ordinary derivative when the dependent variable depends only on one independent variable. You get your you get ordinary derivative. Now in the case of partial derivative, say you have a function that depends upon more than one variable. That is, z is now dependent variable, x and y are your, say, independent variables. Okay. Now variable that is depending upon more than one independent variable. So in that case, you have the concept of partial derivative. So whenever you differentiate the dependent variable, you get partial derivative, and we write like this one, or zx or zy. These are same notation for representing partial derivative. So this is the main definition of your or basic difference between ordinary and partial. In partial derivative, a function or dependent variable depends upon more than one independent variable. Now coming to the definition of partial derivative of fxy with respect to x. Now coming to the definition of partial derivative of fxy with respect to x, and say point is x0, y0. So the partial derivative of fxy with respect to x at point x0, y0 is given by, we usually have a notation like this one. You have del f by del x at point x0, y0, and this is given by dy dx f of x y0. This is one of the representation of partial derivative. What is that? Simply the ordinary derivative of function fx comma y0, because you know when you differentiate partially, or when you have partial derivative of f with respect to x, where f is a function of x and y, then you keep y constant. You treat the variables y constant with respect to x, because x and y are independent variable. Here x and y are independent variable. You have something like fxy. Here x and y are independent variable, so you treat x and y, when differentiating with respect to x, you treat y as constant. So we can also write this partial derivative as ordinary derivative of function fx comma y0. We put the value y0 at the point x equals to x0. You differentiate it, and then finally you put x equals to x0. In the terms of limits, you know very well the definition of partial derivative is x naught plus h y naught minus fx naught y naught upon h, provided limit exists. So this is the definition from limit point of view, how we define partial derivative. So partial derivative, I am representing partial derivative by short notation PD. So partial derivative of fxy with respect to x at x naught y naught gives a rate change of fxy with respect to x when y is kept fixed at value y naught. So basically, partial derivative of f with respect to x at any of the point gives you the rate change of fxy with respect to x when y is kept constant at y naught. So this is what the partial derivative. Remember that before this you did ordinary derivative. So you know ordinary derivative. This gives you a rate change of y. This gives you a rate change of y with respect to x. How y, at what rate y changes with respect to x. Similarly, here when we are dealing with the partial derivative, then this gives you rate change of fxy with respect to x, and y is fixed at y equals to y naught. Another thing that will be used in your topic directional derivative, that we will be doing after chain rule, the concept of directional derivative. We have a definition that will be used there. The definition or some idea of partial derivatives which we are writing here, that will be used there. And the idea is that it gives a rate change of fxy in the direction of I cap or x-axis, along x-axis at point x naught y naught. That is, the partial derivative of fxy with respect to x at point x naught y naught gives you rate change. Not what we were saying it gives you rate change, but if we see the direction, why we are here discussing direction, that because it is going to be used in another topic of directional derivative. So this is the base of that concept, that partial derivative of fxy with respect to x gives you rate change of fxy in the direction of I cap or x-axis. So this is the partial derivative of fxy with respect to x. Now I am just here giving you the geometrical interpretation of your partial derivative of f with respect to x at point x naught y naught. So and that you can then correlate with the partial derivative of f with respect to y. The same geometrical interpretation you can then correlate. So geometrical representation of partial derivative of fxy with respect to x at point x naught y naught. Now here it is, we are going to see. Before that, you know very well dy dx. This gives you the slope of tangent to the curve, at the given point, the point where we are going to find the derivative dy dx, where whatever the point is. So you know very well that dy dx gives you slope of the tangent to the curve at a given point. Again here partial derivative of fxy with respect to x also gives you the slope. What is that slope? So let me just first write here, and then I will show you in the figure. Geometrically, the partial derivative of fxy with respect to x at point x naught y naught gives slope of the tangent to the curve. Here this fxy, you can write it like z equals to fxy. Okay, you can write it as z equals to fxy. So it gives you the slope of tangent to the curve z equals to fxy naught, and from where this curve comes, it comes from the intersection of surface z equals to fxy and plane y equals to y naught. So it gives you the slope of tangent to the curve z equals to fxy naught at point P x naught y naught and your z naught. Your z naught is your f x naught y naught. This comes from here. At point x naught y naught z naught, because z equals to fxy represent a surface and it will be in three-dimensional space. So the point is your x naught, y naught, z naught, where z naught is basically fx naught, y naught. You put x naught, y naught for it, you get z naught. At point this P, x naught, y naught, z naught here. And also you can write in the plane, we have written above here, that is the intersection of surface and plane, but again in the plane. So in short, let me summarize this. Partial derivative f with respect to x at point x naught, y naught gives the slope of tangent to the curve z equals to fx y naught at point this in the plane y equals to y naught. I am just writing it here. Partial derivative of fxy with respect to y at point x naught, y naught. So this is written as your x naught comma y naught, and here it is x naught comma, because you are now going to fix your x naught, so you can simply say that partial derivative of f with respect to y is the ordinary derivative of f x naught comma y, because you keep x constant or you put if x equals to x naught, it is not going to affect the answer. And in terms of limit, it is given as limit x tends to 0 f x naught yes, y naught plus x minus x naught comma y naught upon x, provided limit exists. So it gives a rate change of fxy with respect to y when x is kept fixed at value x equals to x naught. So this is the definition or rate change what partial derivative of f with respect to y gives. It gives rate change with respect to y when x is kept fixed at x equals to x naught, and also it gives you slope, and also it gives you the rate change. It also gives you rate change of fxy in the direction of j cap or y axis at point x naught, y naught. In the direction of j cap, it is the reason why, because we are differentiating with respect to y. Y is variable, x is fixed, so we can't find the rate change in the direction of I cap here. Only y is varying, so we get rate change in the direction of j cap. So these are the definition. Before moving forward, I just noticed that here I have made a mistake. Y equals to mx. I should be writing it here. Either I should have taken here y equals to, this is your, no, this is fine. In the previous question, yes, here it is. I should have taken here either m square x, then it is correct, m square x, okay. Otherwise I am taking y equals to mx, then I should be writing in place of m square as m. So just please correct it, okay. So if it is mx, let me write it as mx, then it should be your m. So these should be m, like this one, x square, and this is your m. So this is I just noticed this correction here, 1 plus m and 1 minus m. Okay, now coming again to the examples of your partial derivative. Let us do some examples of your partial derivative. First example, find the partial derivative of fxy is equals to tan inverse y upon x with respect to x and y both. We have to find the partial derivative of fxy with respect to, with respect to x and y both. So let us solve it. First, let us take it with respect to x. So you know the differentiation of tan inverse x, that is here, and then dy dx of y upon x. That is what we have to do now. So this gives you x square plus y square, and this differentiation gives you minus y upon x square. So you get partial derivative as minus y x square plus y square here. Similarly, if you find the partial derivative with respect to y, then this gives you, again you differentiate with respect to y, you get this one, and then dy ordinary derivative with respect to y. This gives you x square plus y square, and with respect to y it is 1 by x, so you get x upon x square plus x square. So this is the simple method, that's how we can find the partial derivative of given function. Now I come to the another question for partial derivative. fxy is equal to x raised to power y. Find f double partial derivative x and find f double partial derivative with respect to y. I am doing the first part, f partial derivative with respect to x. Now see here it is your y, x, y minus 1. This is the first partial derivative. And now if I have to find the double partial derivative, I got this thing, y minus 1, x, y minus 2. So this is the second partial derivative with respect to x. In case I am differentiating with respect to y, then this gives me your ln x. It is of the form y is equal to ax form. Here we have to find the derivative. So this ln x and x raised to by fx, and again if differentiate it again with respect to y, then we will get ln x whole square x raised to power y. So this is how we can find the partial derivative. Now here we are using the notations of double partial derivative. So before moving forward, let me just tell you in short about the notations that we use for partial derivative. So usually we represent the partial derivative. Say you have a function fxy, we represent the partial derivative as this one or this one, and if at some point write like this one, or simply this one. So these are the same notation. This is the partial derivative f with respect to x. It is at some point or at some point. You can write like this one. Then for double partial derivative, it is something like this one. It is somewhat like this. Similarly, for double partial derivative with respect to y, is same thing. We have this thing. Okay. Here you have fxy. Now sometimes what happens, usually some of the in books, I don't know what in Thomas Finney what we are following, we usually take the derivative from here, that this derivative is coming first and then this derivative is done in the last. So x, it is derivative is taken first. So that is, you have to write it like this one, so that when you differentiate it, actually it comes out like this one. That you differentiate first with respect to x, whatever it comes, then you differentiate it with respect to y. Now similarly, fyx, it means first you differentiate with respect to y and then you differentiate with respect to x. So it should be written like this one. So this is basically first differentiation with respect to y and then differentiation with respect to x. So these are some of the notations so that we will be using in our theory of partial derivatives. Now, example 3 deals with the partial derivative of implicit function. Partial derivative of implicit function. Now, in these cases, what is the question? How it is asked? Let me write it. Find dz by dx if yz minus ln z is equal to x plus y. Define z as a function of two independent variables, x and y. Okay. So you have to find partial derivative of z with respect to x. Okay. And but function is not given. It is given in implicit form. Yz minus ln z is equal to x plus y. That is implicit form where it can't be, you haven't written like z equals to fxy form. They are not separable. Z equals to fxy form, you are not writing in that way. So it is the form that is given, implicit form, when you can't write z equals to fxy in this form. So for such type of questions, what you do, whatever has been asked, the derivative, you differentiate the both sides of the given equation, implicit equation, whatever is given. So here, differentiate both sides with respect to x, so you get y. Now be careful, here z is a dependent variable, and x and y are two independent variables. So these, please keep it in your mind that x and y are independent, only z is dependent. So when you differentiate with respect to x, y will be treated as constant. Okay. So this becomes y dot del z by del x, y is treated as constant, minus ln z, 1 by z del z by del x, x 1 and y. Since y and x are independent, so this is 0. So this gives you del z by del x, yz minus 1 upon z is equal to 1, implies del z by del x is z yz minus 1. So this is the solution of your question in which you have been given to find del z by del x, but z is given not in explicit form, it is given in the form of equation in implicit form. So it is the way that we can find out the solution of such equations, or we can find out the partial derivatives. Similarly, we have another question. You can try this. You have here example 4. Find same question, I am not writing a statement, I am just writing here the equation xy plus z cube x minus 2yz equals to 0. So I am now writing just the expression. So in this expression now you have to find del z by del x. Find same question as was asked in the last example. So del z by del x you have to find. Now again, say this is one, differentiate both sides with respect to x. Now let us see what happens. Y is treated as a constant, so y plus 1. Y will be treated as a constant because x and y are independent. Yes, here it is. Now you can see z cube. Okay, so let me just make it more clear that one by one term, because here you will have confusion. So let me first take this term and then take this term so that things get clearer to you. So for first partial derivative, y is constant, so this is y into 1, fine. And then here z and x, so first I take z cube as such, differentiation with respect to 1, x, that is 1, then you keep x as such and differentiate with respect to x, you differentiate z cube, this gives you del z by del x. Now here again y is constant and del z by del x, this is equal to 0. So this gives you y plus z cube plus del z by del x, 3x z square minus 2y is equal to 0. So del z by del x, this will comes out to be y plus z cube upon 2y minus 3x z square. So this is the required solution. Yes. So in this way you can find out the partial derivative of a given implicit expression where z equals to fxy form is not given. So this is the way to find the partial derivative in case of implicit functions. Okay, with this I now close this lecture, and in the next lecture we will start the chain rule. Okay, thank you. Thanks a lot.